energy storage systems, grid integration of renewable energy sources, and grid forming inverters. We are very fortunate to have such an eminent speaker as today's guest. Now I request Dr. N.K. Swaminaidu to address the participants. Sir.
పైన పెట్టుకుని పెడతాం. ఐదు దీనికి చేతితో రాయొచ్చండి. ఇది ఏమో అవసరం లేదు, నార్మల్గా ఉంటే పర్వాలేదు, లేకపోయినా ఓకే. ఇలా ఫుల్ స్క్రీన్ చేసాను. ఓకే ఓకే, కానీ ఫుల్ స్క్రీన్ చేస్తే ఫస్ట్ ఏమో కాదు, రావట్లేదా? ఇదే ఫుల్ స్క్రీన్. ఓకే. ఫైన్, ఓకే. దీంతో చేంజ్ అవుతుందా? లేదు, ఓకే. లేకపోతే అవసరం లేదులేండి మోస్ట్లీ. రాదు, అలాగే పర్లేదు. ఓకే ఓకే. గుడ్ మార్నింగ్ ఆల్. గుడ్ మార్నింగ్. బట్ ముందుకు వచ్చేయండి. అల్లా ఎవరు వస్తారా ఇక్కడికి? సార్ ఎవరైనా ఉన్నారా సార్ ఇక్కడ? ఎవరు లేరా? ముందుకు వచ్చాను, పర్లేదు, ఏం కాదు. నేను క్వశ్చన్స్ అడగాను. 1 minute, నో ప్రాబ్లం. Okay. Okay, I'll start my presentation. వస్తుందా, వినిపిస్తుందా? లాస్ట్. ఓకే. For morning session, I'm going to start with double-fed induction generator for wind energy conversion systems. In this, I think mostly, first of all, we want to see what is wind energy conversion systems. Then they will try to see first introduction to wind energy conversion systems. Then we'll see how wind can be converted into an electrical energy. Then what are the different topologies. that maybe if you are from electrical, maybe we can understand to convert from wind energy to an electrical energy, we need different uh, generators. Based on the generators, maybe we can divide this total wind energy conversion systems into different topologies. Okay, 10th one. Back. Okay. Okay, right. Then we will see what are the different topologies or different possibilities. From there, we will try to see DFIG. Is the name is DFIG? ఇది రాయదండి రాయదు కదా జస్ట్ ఓన్లీ టు స్క్రోల్ అంతే కదా ఓకే ఓకే ఓ ఓకే 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 రండి ఓకే ఓకే ఇప్పుడు ఓకే ఓకే ఓహో బోర్డు వస్తుంది పూర్తిగా స్లైడ్ మీద రాయలేము ఓకే ఓకే గుడ్ here we will see what is DFIG. DFIG means the name is looking fancy, doubly fed induction generator. I think even I kept it in my introduction slide also, in the starting slide also. It's nothing but wound rotor induction machine. It's normal induction machine. You have slip rings that are available to you. Yes, you may have studied wound rotor induction machine. Yes, and the DFIG we will see how the grid connected DFIG and how the standalone DFIG. In this first one is regarding wind energy conversion systems. If you see here, I think everybody of you may have already seen this wind energy conversion systems. In this, these are the rotor blades, and this is very huge turbine structure. I think you may have seen in the movies, or you may have seen some of the people, I don't know. But this is very huge, and this is falling, this is just standing on the such a big huge tower or structure, in that even if someone is standing here, that is looking very small here. It means by that you can understand how big it is. It has some rotor blades, and due to wind it will start rotating it. Suppose if it starts rotating it, then you have mechanical energy now. To convert into an electrical energy, you have now a generator. Before that, if these are the rotor blades, and this is called, sorry, this is the problem, this is rotor hub, and this hub for and this rotor blade, they are connected using a motor here. You have normally motor here also, so that you can turn this blade. Okay, sometimes if wind is coming very heavily, then if you want to shut down, maybe you keep it previously. Suppose if wind is hitting here, it may move. Suppose if this is like this, if wind is coming, it will not move that much speed. Yes, so that you can change the direction here, and so that at when very high wind speed is there, you have to protect it. For that, here you need pitch angle. This is called normally a motor. You can change the motor, you can change the direction, means a little, maybe some stepper motor type of things will be there. You can change the angle of attack here. And also, if you see here, this is also called, maybe you may have studied, if someone has wind energy previously studied, this is called pitch angle control. And afterwards, there is a shaft here, and even if you see the wind turbine, those are rotating very slowly like this. Even you can see that rotation, very slowly it will rotate. If you have that much slow rotation, and if you want to convert into 50 Hz frequency to connect to the grid or to use, then the number of poles maybe we can calculate. How we can calculate number of poles? If you take synchronous speed, that is ns equal to 120 f by p. Ns equal to 120 f by p. Yes, in that you want 50 Hz frequency, and suppose it is rotating at 10 rpm or 20 rpm. And from there, if you calculate the frequency that is coming will be very less. The frequency that is coming is very less. So the problem here is, so at low rotor speeds, you will not be able to generate the voltage at desired frequency. So you need to increase the speed. That's why you have here gearbox, and that will increase the speed so that this shaft will rotate at higher speeds. And when it is rotating at higher speed, now depends upon the poles of this machine, the frequency will be generated according to the desired frequency, 50 Hz or something. Maybe you may be thinking, I can increase the number of poles. If that is rotating at very low speeds, maybe we can increase the number of poles. But we can increase the number of poles, but due to the availability of space and due to very big means the limitation of that space, you cannot accommodate so many poles into this machine. So normally the thing they do is, normally they go for step down, okay, in the gearbox, and there will be an increase in speed. The number of poles are normal only. Then the frequency will be according to it, maybe 50 Hz or something. Okay, and also this is wind speed measurement. This is called anemometer, and we will see that what are the different challenges for this. Different challenges. These are, suppose if you want to connect to the grid. We know that for the grid, the voltage and frequency is fixed. Yes, the voltage and frequency is fixed. But wind turbine wind speed is not constant always. Sometimes you may have high wind speed, sometimes you may have less wind speed. Okay. So if you have high wind speed and low wind speed, then the frequency that is generated is also variable. Yes, because number of poles are fixed. If it is rotating at different speed, the frequency will be different. Yes, the frequency will be different. So there is a need to convert this variable voltage, variable frequency into constant voltage and constant frequency to connect to a grid. Yes, because as you have variable rotor speed, obviously you need some mechanism. Okay, that mechanism is, this is the variable wind power is the problem. So you need some mechanism to convert variable voltage, variable frequency into constant voltage, constant frequency. That's where comes our power electronics. Power electronics, there is some mechanism will be there. Otherwise, there may be two converters will be there to convert this variable voltage, variable frequency into DC. And from that, once you got DC power, you can generate whatever voltage, whatever frequency you want. You can generate it directly, because that is an inverter. Inverter, if you have DC, the AC voltage and frequency, you can generate whatever you want and connect to the grid. Okay, so that is actually here the challenge. The other is increased penetration of wind energy. Here the problem is, suppose wind energy penetration has increased, suppose out of total installed capacity of our Indian total power generation, suppose if this wind power has increased, then the problem there is, wind, we don't know when you will have more, when you will have less, but you have to give always power to the consumers. Okay, so due to this variable nature of wind, the problem is, if now we have around, I think 5%, 6% of the wind, I think even less than 4% of the wind total installed capacity. Suppose if we assume that has increased to 15%, otherwise total renewable has increased more than 50%, then you never know when there is, suppose solar is there, wind is not there, solar is not there, you can't guarantee the power. Okay, that's the problem. And also weak distribution network. This is major, I think, research topic, like where your wind turbines are connected very remotely. Those are very far from the normal city centers. There, if you are very far, then those wires carry very, if you are carrying that power very remote, then you will have, due to the line inductances, here the voltage will be reduced, and also due to this source impedance, that is called weak grid. The grid will become weak and you will face so many problems. And also, if you see, most of the wind turbines are connected to induction machines, not synchronous machines. Yes, now recently they are connecting to PMSG, permanent magnet synchronous generators, but most of the previous, around 50% of the installed wind turbines now, 50% are now with running on induction machines. If they are running induction machine, of course, if they are induction machine, you need reactive power. That is the problem. Suppose if that is synchronous machine, you give DC supply, you can change the excitation, you can change the reactive power. Yes, you can change the with excitation DC or whatever it is. You can do it, but in case of induction machine, you need a reactive power. Even if you take a wind turbine, I think as far as my knowledge, in 2016, if I see, the largest wind turbine was 15 megawatt. 15 megawatt single piece of a wind turbine is there. And if I assume my induction machine has 0.8 power factor, if my induction machine has 0.8 power factor, then cos phi is 0.8, then sin phi is 0.6, sin phi is 0.6, then 15 megawatt into 0.6, it's around 9 MVAR. 9 MVAR reactive power is required to run that induction generator. How, where can we generate? Okay, that's where your capacitors are coming, but these capacitance are fixed. These capacitance are fixed. If there is any problem in the power generation, then anyway, the burden will be very high if you are using wind turbines. I think before understanding wind energy conversion system, first of all, we should understand this wind turbine power characteristics. This is y-axis is power, the x-axis is speed. These are the different curves. These are different curves for different wind speed. The outer one is for particular wind speed. This one is for particular wind speed. This characteristic is for a particular wind speed. Even if I assume my wind speed is constant, that is 1 per unit, wind speed 1 per unit, if I assume, it doesn't mean the power is constant. If I have particular wind speed, 12 meters per second wind speed, if I assume, even then your power is not constant. If you have, suppose this 1.0 per unit, this is the curve you will get. You may get power of this one minus 0.4, you may get power of this 0.6, you may get power of 0.8, you may get power of 1 per unit. Even my wind speed is constant. Even my wind speed is constant, I may get different powers based upon this rotor speed. Suppose if I run my wind turbine at this 1.0 per unit rotor speed, I will get this power. I'm repeating, my wind speed is constant, but still if I change my rotor speed, my power is changing. Sometimes it may be 1.0 per unit, sometimes it may be 0.8. Suppose if I run my wind turbine at 0.8 per unit rotor speed, then I may get this much power. If I run my wind turbine at 0.6 per unit, I may get power of this much, around 0.5 per unit. Okay, this is one thing. It means now we should understand, even my wind speed is constant. If I want to get maximum power, then I have to run at a particular speed, only one speed. If I run at 1.0 per unit rotor speed only, then only I will get the maximum power. Suppose by chance or any problem, if it is running at 0.8 per unit, the available wind power is this much, 1.0 per unit, but I may be getting very less. I may be extracting very less. So by this, we can understand you have to run at a particular wind rotor speed to extract maximum power. And also, that is one problem. I am telling, even my wind speed is constant, my power is not constant. That is one problem. The other problem is wind speed is itself not constant always. Sometimes you may have 1.0 per unit wind speed, sometimes you may have 0.9 per unit wind speed, and suppose if my wind speed is 1.0 per unit, then I can tell my turbine, oh, run at 1.0 per unit so that I will get the maximum power. I can instruct that. Now suppose wind speed has suddenly changed. Wind speed has came to this 0.9 per unit. Then I have to tell my wind turbine, now don't run at 1.0 per unit, now run at 0.9 per unit. Now run at 0.9 per unit so that I will get the maximum power. Suppose my wind speed has changed now. Suppose this is running at, my wind speed is 0.6 per unit. Then I will tell my wind turbine to run at 0.6 per unit so that I will get the maximum power. So by this maybe we can understand if your wind speed is changing, then you have to change your rotor speed. You have to change your rotor speed. If wind speed is changing from one curve to another curve, then you have to change your rotor speed such that you achieve maximum power. That's why this is called variable speed wind energy conversion systems. You have to run at variable speeds for achieving maximum power. Maybe I will tell you one more option, like suppose this is running always at 1.0 per unit. Always at 1.0 per unit irrespective of my wind speed. Then suppose this is a vertical line, I am always running at. Suppose my wind speed is 1.0 per unit, it's good, it is giving maximum power. But if my wind speed has become 0.7 per unit, then I may be even my available power is this one, but I am generating this much. Okay, so this is called fixed speed wind energy conversion systems. There you are not achieving any maximum power. Okay, because here this is not maximum power point, this is not the maximum power point, this is not the maximum power point. Only for this particular wind speed only, this is maximum power point. Okay, based on this, I think we can conclude two things. One is fixed speed wind energy conversion systems and variable speed wind energy conversion system. Suppose if this is variable speed wind energy conversion systems, you run at different rotor speeds for different wind speeds. If your wind speed is changing, you change your rotor speed so that you will get the maximum power. Okay, in fixed speed wind turbine, irrespective of my wind speed, I will run at a particular rotor speed always, but the problem there is I won't get maximum power always. I won't get maximum power always. So if you see here, these wind energy conversion systems there are two types. As I mentioned, this is fixed speed, this is variable speed. In this variable speed, we are achieving maximum power. For different wind speeds, we are running at different rotor speeds for achieving maximum power. But for this fixed speed, you are always running at a particular rotor speed, so you are not getting any MPPT. In this variable speed wind turbines, here we are telling there are two types. One is with gearbox and without gearbox. There may be some cases where without gearbox is also possible. If you don't have gearbox, the speed will be less. Yes, if you don't have gearbox, the speed is less. If speed is less, to attain certain frequency threshold, you should increase the number of poles. Yes, you should increase the number of poles, because as your speed is less, to attain certain frequency, you have to increase the number of poles. In all machines that is not possible, but in permanent magnet synchronous machines, you will have freedom to increase the number of poles, because the thing is, if you have permanent magnets, maybe that can be fit in. But if you have wound rotors, if you want to get the same pole using electromagnet, how we can get poles? Just by wounding some coils. Yes, if you want to wound coils on some magnetic material or any of the metal anywhere, then you need more space. So normally PMSG you can increase number of poles, but in other machines that's not possible. The one more thing is, maybe I can do something like I may be getting 10 Hz frequency generated from my generator, but you can always make the 10 Hz frequency into DC by using some conversion AC to DC converter, and from that DC now you can generate 50 Hz frequency, whatever you want. Suppose if you are using AC DC DC AC structure, then you can generate at lower frequencies also. Even if you generate at lower frequencies, you can convert into the required frequency by using these power electronic converters. Here you have that flexibility, so you don't require any gear. The biggest, if you see the wind turbine, the losses are mostly mechanical, most of significant losses we can tell. The significant losses are mechanical losses. If you reduce this gearbox, you can reduce some of the losses. These are different. With gearbox, these are different, depends upon the machine you are using. Suppose I may be using wound rotor synchronous generator. SCIG means squirrel gauge induction generator. This is normal squirrel gauge machine. And this is wound rotor induction generator, wound rotor induction machine we are using. Any of this we can use. We are just classifying based upon the machine we are connecting. Okay. Just if we see fixed speed wind turbines now. In fixed speed wind turbines, this is squirrel gauge induction generator. This was coupled to wind turbine. And if you see the rotor, if you see the stator, that was almost connected to the grid. This is grid, almost connected to the grid. And with the help of, this is a transformer, this is starter. Starter means this will come only in the starting. Okay, later that will be sorted. Later you will bypass this. Okay, this box will come only at the starting, and this is some capacitor that was connected parallel. So almost this stator was directly connected to the grid with the help of this starter, and this transformer is just step up and step down. It's not a big deal. Sometimes you may avoid this one also. So this looks very simple. You don't require any converters in between. So this looks very simple. Now what you have to do, run this wind turbine at S, so that your rotor speed is greater than your synchronous speed. You should make sure your speed is greater than your synchronous speed, so that now this induction machine will enter into generation mode. Yes, you make sure your speed is greater than synchronous speed. This will enter into generation mode, and the power is generated. Once the power is generated, that will fed to the grid. That's very simple. Okay, maybe how you can change the speed. Now, with the help of this gearbox, I mentioned before, by changing the gearbox, and also by changing the pitch angle here, you can change the rotor position. Yes, by changing this, somehow you make your speed greater than synchronous speed, and this will enter into generation. This will be fed to the grid. But one more thing, that is good, the power is generated, but this is an induction machine, so it needs reactive power. Otherwise it can't produce any voltage. So the reactive power, suppose if I don't connect this capacitor, it will start drawing the reactive power from the grid. Suppose even if I make my speed greater than synchronous speed, it is entered into generation mode, induction generator. Now it is generating power, good, active power is generating, but it will start drawing the reactive power from the grid. If it is taking reactive power from the grid, the problem there is, as I have mentioned, these are very huge machines, and that huge reactive power, if you start drawing from the grid may collapse. The voltage instability problems may occur. So you have to connect a capacitor here to supply the required reactive power. That is mandatory part. this connecting capacitor is mandatory part to supply the reactive power. Even without this capacitor also, this can generate power and this can give to the grid, but the reactive power will be taken from the grid. Okay, but that is not recommended. The one more problem with this is, I mentioned, this is running at a fixed speed. Yes, this is running at a fixed speed. So it is not operating at maximum power point always. This is not operating at maximum power point. Yes, the variable speed wind turbines always operate at maximum power point, but this won't operate at maximum power point. So even the available power we are not able to give to the grid. That is not good. Yes. So this is not so efficient, but the advantage is just there are no maintenance required, and even if I see the installed wind turbines in Gujarat and some of the places in 10 years before, almost all wind turbines are of this nature only, because once installed and forgot. If suppose wind speed is more, it will give power, okay, otherwise no. It means you don't require any frequent maintenance to this. That's why even people are still bearing this, because even though this is not giving maximum power always, sometimes efficiency is we can compromise, but already they may got return on that. Now if you generate power good, otherwise also no problem. So most of the older installations are this fixed speed. The advantages: simple and low cost, cheap and low maintenance. But the main problem is mechanical stress, because even if your wind speed is changing always, you have to run at a particular fixed speed always. That too, you are depending on this gearbox and this pitch angle. So you have so much mechanical stress, so much mechanical stress. You have to change the speed. And power factor is the problem. Now comes the variable speed wind turbines. In variable speed wind turbines, I have mentioned before also, if your wind speed is changing, you have to change the rotor speed. Yes, if wind speed is changing, you have to change the rotor speed. If you are running at different speeds, then the frequency is obviously different. Previous case, you are running at fixed speed, so your frequency is good, 50 Hz. Now for this variable speed wind energy conversion system, for achieving MPPT, you are running at different rotor speeds. If my wind speed is 12 meters per second, I am running at some particular speed. If my wind speed is 8 meters per second, I am running at different rotor speed. So if my rotor speed is changing always, then my frequency is changing always. So now you will get variable voltage, variable frequency. Now to convert that into fixed voltage, fixed frequency, you need some power electronics converters. Okay, that's the main thing we are going to see how this variable speed wind energy conversion system will be done. For getting this maximum power, first of all, you should know what is the wind speed. I have mentioned before, if I know my wind speed, I can tell, oh, you run at particular rotor speed. If I know my wind speed, I can tell what is the rotor speed you should run. And also generator characteristics, you should know, depend which machine you are using. And also rotor characteristics means these are wind turbine characteristics. If I know wind turbine characteristics, then only I can tell at what speed I should run. So this is a wind speed. If this is a wind speed, there is a lookup table, then I can tell at what rotor speed it should run, and inside you will have different controllers. You will have different controllers inside. Now it comes the variable speed wind energy conversion system. In this, I mentioned the problem here. This is variable voltage, variable frequency. This is variable speed wind turbine. As this is a variable speed wind turbine, it is running at variable rotor speeds. Suppose if it is running at variable rotor speed, the voltage and frequency that is generated is variable, and this grid frequency and grid voltage is constant. So you have to use this converter scheme. You have to use this converter scheme to change from variable voltage, variable frequency into fixed voltage, fixed frequency. So you have to convert from this AC to DC and DC to AC. One more thing here. Kuchan. One more thing is this is an induction machine. So this is working as a generator, but still it requires reactive power. It still requires reactive power to generate voltage. So the reactive power, the converter here should supply the required reactive power. Okay. Suppose my wind turbine rating is 1.0 kilowatt. Suppose 1 per unit speed, 1 per unit power. Then my generator is 1 per unit active power. Now my converter, this converter should carry the same 1.0 per unit power, and this converter also should carry 1.0 per unit power. So the power electronics that is required to convert from AC to DC and DC to AC are the combined is 2.0 per unit. If my rating is 1 per unit, then this power electronics rating is 2.0 per unit. In addition, any reactive power requirement. Now, this is with PMSG. The only difference between the previous induction generator and PMSG are this PMSG, it won't require any reactive power. And so the converter rating will be reduced little bit, but still the power rating, suppose if this is 1.0 per unit and this is also 1.0 per unit plus this is also 1.0 per unit. Now it comes to the main topic, which is doubly-fed induction generator, or otherwise wound rotor induction machine. There your converters are not connected in the stator side, but these are connected in the rotor side. If you see this is DFIG, means wound rotor induction machine. In this wound rotor, the stator part was directly connected to the grid, and in the rotor you have two converters. That were connected. In the previous case, if you see there, suppose for simplicity, if you take, these are connected in the stator. These converters are connected in the stator, but in this case, your converters are connected in the rotor. How does it matter? Yes, it matters a lot. If my slip is less, then my converter rating will be less, because in rotor side, if you see, you know that, if my air gap power is there and my rotor power is slip times my air gap power. Suppose if my slip is plus or minus 0.3, if my slip is plus or minus 0.3, then suppose my PG is 1, then my PR is 0.3. So here the power flowing is 0.3 per unit, but in the before case the power flowing is 1 per unit here. So the converter rating is 0.3 per unit here, 0.3 per unit here. So the total power electronics required is 0.3 plus 0.3. 0.6 per unit converter rating is required here. But in the before case, 1 plus 1, 2 per unit is required. But in this case, only 0.6 per unit is required. It means your converter rating is becoming almost 1 by third. Okay, your converter rating is becoming 1 by third. So this is very good, because suppose if my machine is 10 megawatt machine, if my machine is 10 megawatt machine, in the previous case, the converter that is required is 20 MVA. 20 MVA converter is required. But in this case, for 10 megawatt, you require 3 MVA plus 3 MVA, 6 MVA. There it is 20 MVA. So the cost will be very less in case of DFIG as compared to other topologies. One more thing maybe we can see here. Here the power that is coming is 1 per unit, and here the power coming is 0.3 per unit. So overall power that is feeding to the grid is 1.3 per unit. Here the overall power that is feeding to the grid is 1 per unit plus 0.3 per unit, 1.3 per unit. So with the converter rating of 0.6 per unit, you are feeding power of around 1.3 per unit. So that is very much advantageous, because the converter rating is very less. The other thing is, wait, I think maybe I'll stop. Let them settle down.
रिसर्च गरेर बनाएको छ फोटो त नपर्ने पनि टेन्सन नपर्ने
Okay. In this case, one advantage I told here, for getting power of 1.3 per unit, your power electronic converter that is required is 0.6 per unit. That is very, it means the converter requirement is very less. That is the one advantage. The other advantage is the rotor voltage is also slip times stator voltage. The rotor voltage is also slip times stator voltage. Suppose if my converter voltage is 11 kV here, the stator voltage is 11 kV, then it will be 11 kV into 0.3. 11 kV into 0.3. Here the required 3.3 kV. Yes. So these converters need to handle very low voltages as compared to the previous topology. Here the converter that is that are handling the voltage is very less. The voltage requirement is less, first one. The power requirement is less. That's why this is the topology that people have almost till now people are mostly using for wind energy conversion systems. And maybe I can tell like around 50% of the installed wind turbines all over the world, 50% of the installed wind turbines are of this DFIG nature only till now, because the converter rating is very less. Suppose if we go to PMSG, permanent magnet synchronous generator, in addition to this converter rating, one more thing is permanent magnets are required. Those are also very rare earth magnets. The machine is also costly, and also the converters are also costly. That's why people are going for this. So as I mentioned, let them go. Later I will. మళ్ళీ వాళ్ళు ముందుకు వచ్చేవాడిని. అట్లీస్ట్ కొంచెం కొంచెం ఫేస్లు కనిపిస్తాయి, కొంచెం లాస్ట్ మళ్ళీ ఎవరు వస్తారండి
ఏం కాదు సార్, ఏం కాదు, తీసుకొచ్చాను.
వాళ్ళు ముందుకు వచ్చేయమంటే మరి కొంచెం ఆ లాస్ట్ ఇక్కడికి వచ్చేయండి, ముందు వదిలేసి మిగతా కూర్చోండి, వచ్చేయండి. పర్ఫెక్ట్. మీరు ఎవరు థర్డ్ ఇయరా? ఏమన్నా అర్థమవుతుందా? అర్థం అవట్లేదా? ఇందులో ఇండక్షన్ మిషన్ తప్పించి ఇంకేం లేదుగా, ఇండక్షన్ మిషనే చెప్తున్నా. ట్రై చేయండి. ఏ కొంచెం అర్థమైనా చాలు, ఓకే, పూర్తిగా అర్థం అవుతుంది, అలాగే నాకు తెలుసు. ఓకే, దిస్ మీకు ఫైనలీ ప్రాజెక్ట్ చేయడానికి పనికి రావచ్చు ఇవి, ఓకే. అట్లీస్ట్ హార్డ్వేర్ మీరు చేయలేకపోయినా సిమ్యులేషన్ అయినా చేయొచ్చు, ఓకే. డిఎఫ్ఐసి సిమ్యులేషన్ అవి చేయొచ్చు మీరు. The DFIC, the main advantages are, if you see, the converter rating is very less and efficiency is also improved because you are handling less converter rating, so the losses will be less. And one more thing is, here I think one point you have to clear. I told 0.3 per unit, I fixed it. Why I have restricted my slip to 0.3 only. Slip is 0.3 means the speed is 0.7 to 1.3 per unit. Suppose if my slip is plus or minus 0.3, then my rotor speed is 0.7 per unit to 1.3 per unit. I told my machine will run at only in this 0.7 per unit to 1.3 per unit only. Why? Because my power P equal to the wind turbine power. This is Cp lambda beta. This is mechanical side of rho A V cube. V is the wind speed. So my power is proportional to V cube, wind speed cube. Suppose if I assume my V is almost V and omega varies in the same proportionate, P is proportional to omega cube. Suppose if my rotor speed is 0.7, if my rotor speed is 0.7, then how much will be the power? How much will be the power? It's around 0.3, I think. Yes, 0.343. 0.7 into 0.7 into 0.7. That is 0.343. This is the power. Suppose if my rotor speed is 1.3 per unit. If my rotor speed is 1.3 per unit, then my power is 1.3 whole cube. How much? 1.3 into 1.3 into 1.3 means it's around, I think, 2. The power is here, if I change my wind speed or rotor speed between it's 2.15. Yes, I approximately taken it as 2. Yes, so this my rotor speed is changing between 0.3 to 2 per unit. If my wind speed is changing 0.7 to 1.3. Suppose if I make this 2 per unit as 1 per unit, I have scaled down, then this 0.3 will become 2 to 1, it means it's 0.17. So my power is changing between If my rotor speed is changing between 0.7 to 1.3, my power is changing between 0.17 to 1 per unit. It means I am getting the whole power. My power is, suppose if I run at 0.7 per unit, I will get this much power. If I run at 1.3 per unit, I will get this much power. So why I should go down, further go down? Because only running in this range, 0.7 to 1.3 per unit, I am almost getting the power. I am almost getting the power. Even if I want further down, before 0.17 per unit also, your cut-in speed will be very less. At low speeds, you have to extract power. Then losses will be more. And another problem is, suppose if my slip increases, if I increase my slip, then my converter rating will increase because my PR is S times PG. If I restrict my S to plus or minus 0.3, my converter rating is 0.3 only. Suppose if I make it 0.4, then I have to increase my converter rating. So I won't get any much advantage even by increasing the converter rating, just going below this power range. So normally people fix the power rating as this one. This is overall doubly fed induction generator. This is the grid, and this is an induction machine, wound rotor induction machine. This was running with wind turbine. Now in the rotor there are two converters that are connected. Theoretically, you may tell you get voltage from DC to AC, but even if you are, maybe you may have studied PWM, pulse width modulation. Yes, if you know PWM, then the generated voltage will be in pulses, but it's not pure sinusoidal. To get that into a sinusoidal, you need some filters, and these are the filters to convert back into this pulse width voltages into sinusoidal voltage. So this is a filter here. Then you can ask why there is no filter here. Here you have rotor winding inside, so the rotor winding has some inductance. Okay, so you don't require any filter here. Okay, now this is rotor side converter. This is, I am telling always, like you have to change your speed. I am telling always. Yes, I think in discussion I told so many times you have to change the speed. But in mechanical side, if you want to change, you have to change with the help of gearbox and pitch angle. But I told that there is a problem with the mechanical stress. Now, in all these variable speed wind energy conversion systems, they change the speed not mechanically, but electrically. Electrical speed can be changed if you see plus, okay. Okay. We know this equation Tm minus TL J d omega by dt. You may have studied in almost all the machines. This is motor torque, this is the load torque, this is the speed, this is moment of inertia of the system. Now if I want to increase my speed, then I have to make my motor torque greater than load torque. Then this acceleration will come, the speed starts increases. If my motor torque equal to load torque, suppose if my motor torque equal to load torque, then speed will be constant. Whatever the speed it is running, it will run at that speed only, it won't change. Yes, suppose if it is at 0, it will stay at 0. If it is running at a particular speed, it will run at a particular speed. Suppose if my machine torque is less than load torque, my speed decreases. my speed decreases. So now from this we can understand my motor, if I want to change my speed, I have to change the load torque in case of a motor. But in case of an electrical generator system, suppose there is a mechanical power you are getting from the wind turbine, and suppose this was a generated power. If I am giving some power, mechanical power PM, and electrical power is generated here, this was connected to a grid. Suppose if I make my electrical power, less than my mechanical power, suppose here we have good amount of power, mechanical power, now you have somehow you have reduced electrical power, then the speed will be increased or decreased? Suppose I will write when my PM is greater than PE, the same thing I have written. Now my speed will increase or decrease? Increase? Increase. Because I have power, mechanical power more coming, and I am converting very less electrical power, so the remaining power will try to increase the speed. Yes? Okay. If I make my mechanical power less than my electrical power, my speed will decrease. So by this maybe we can understand, to change the speed, what is in our hand? Electrical power is in our hands. Now I can change my electrical power. I can change my electrical power to change my speed. How I can change my electrical power? Maybe here in this case it is not possible, but suppose if I have there are two converters that was connected to a grid. This is AC to DC, and this is from DC to AC. Now I want to, this was coupled to wind turbine. If I want to change my electrical power, my voltage is fixed here. This is grid. If I change my current, then my power will be changed. Now I can control my current. If I control my current, I can change my, by controlling current I can control my electrical power. By controlling my electrical power, I can control my speed. Okay? So ultimately, by controlling the current here, you can control the speed. By controlling the speed, we can achieve maximum power. Okay. One more thing here is something maybe we can discuss better with this. I can change my stator power. I have to change my stator power with the help of these converters that are placed in the rotor side. These are, because you don't have any control over here. Here you have, what you can change? You can change the voltage and current, whatever you want to change in the rotor side only. But that should affect your stator power. How it is? By controlling the rotor currents. Maybe this is the equation. Maybe I think DQ transformation, I don't know whether you understood or not. in any of the rotor current, this is the rotor current, this is the relation between your rotor current and your stator power. If you change my rotor current ID, if I change my rotor current, my power will be changed. It means here if you see, if I change my rotor current here, my power will be changed here. Okay, so I have to change the current here for changing the power here. One more thing, like the stator was directly connected to the grid, where I will get the reactive power to this DFIZ. Suppose if you are not giving from anywhere, it will draw the reactive power from the grid. It will take the reactive power from the grid and mechanical power will be converted into electrical active power. Active power will be in this direction and reactive power will be coming from this direction. But if you start providing the reactive power by using this rotor side converter, if you are giving reactive power, you are injecting the reactive power into the rotor circuit, then what will, anyway your machine is getting the required reactive power from this converter, so it won't draw any reactive power from the grid. Suppose if you are not giving any reactive power from the rotor, then it will draw completely. Okay, now there are two converters. The first one is RSC, means rotor side converter. With the help of this rotor side converter, maybe I think I have to go back again. This is RSC, rotor side converter. This is grid side converter. I told some series of events or series of equations that for achieving MPPT, you have to change the speed. For achieving MPPT, you have to change the speed. For changing speed, you have to change the electrical power. That electrical power will be changed with the help of this rotor side converter. So with the help of this rotor side converter, this rotor current, I will change the electrical power, and that electrical power will change the rotor speed, and rotor speed will in turn change the MPPT point. Yes, okay. So here all this rotor current. This current will be controlled with the help of this rotor side converter. So by this maybe we can understand this rotor side converter is responsible for achieving maximum work. Yes, by controlling the current here, it is active power is changing, and by that mechanical speed is changing, by that MPPT is changing. That is one thing this rotor side converter work. The other work is it has to supply the required reactive power also. If you don't supply using this rotor side converter, it will be drawn from the grid. So the work is torque control and flux control here, and this grid side converter work is, suppose some power is generated here, it is coming here, and it should act as a simple buffer. It should act as a simple buffer. Okay, just whatever the power is coming, just give to the grid. The work of this grid side converter is just act as a buffer and give the required DC link voltage also. Give the required DC link voltage so that it can actually generate the desired voltage here. Okay. So that's what here I have mentioned. MPPT is rotor side converter is responsible. Act when reactive power also rotor side converter. This is the complete control scheme of a DFIZ. In the laboratory, you don't have any wind turbine. You don't have any wind turbine. I have worked in Delhi. So if you want wind turbine, even if you connect there, you won't get any rotation. You won't get any rotation, and then I can't finish my PhD. So, good. Thank you. Okay, అది కూడా ఇక్కడ పెట్టాము. ఓకే, థ్యాంక్ యూ. ఎంత టైం అయింది చూడాలి ఒకసారి, నేను చూడలే. 12 అయిందా? ఇంకెంత టైం తీసుకోవచ్చు? హాఫ్ అన్ అవరా? 40 minutes. ఓకే, గుడ్. హాఫ్ అన్ అవర్. Okay, the thing here is wind turbine has its own characteristics. I have shown you before the wind turbine characteristics in the first slide. I think I have shown you wind turbine characteristics that will change with, for different wind speeds it will change. But how we can get that wind turbine characteristics in the laboratory? Suppose if you connect a DC shunt machine, if you see this is DC shunt machine. DC shunt machine characteristics are different. Yes, DC shunt machine characteristics are just straight line falling down. If load increases, the speed will drop down little less. Yes, it's almost constant speed machine, DC shunt machine. Yes, okay, but this wind turbine characteristics are different. So these wind turbine characteristics, how can you emulate? Those wind turbine characteristics will be emulated in a DC machine. We have DC machine in the lab that was connected to wound rotor induction machine. These characteristics will be emulated with the help of a chopper. Here we have connected a chopper, and DC machine torque, how can we control? Torque is flux into armature current. Yes, torque is flux into armature current. Now I have taken DC separately excited machine, so my flux is constant. So if I change my current, I can change my torque. If I change my armature current, I can change my torque. So in this armature, I connected a buck chopper here. With the help of this buck chopper, here the armature current is changing, so that I can achieve whatever the torque I want. Now I have kept some microcontroller, and that microcontroller, with the help of that microcontroller, with the help of that microcontroller, I'll feed the wind turbine characteristics. I have written P equal to half rho A V cube. That equation will be in my microcontroller, and that will decide my torque. If I calculate my speed, if I make my P by speed, power by speed, that will be your torque. If I get my torque, and from the torque I can calculate what is the armature current. Yes, torque is power by speed. Now I know how much would be my torque. If I know my torque, I can calculate what is my armature current also. Torque by flux is again armature current. So I will get the required armature current, and this wind turbine emulation is in your microcontroller, and that will dictate what is the armature current, and will control this armature current. This closed loop control, everything will be done in a digital signal processor or other microcontroller. And I have mentioned this is here, currents should be controlled here. So I am sensing the currents here. We keep some current sensors there in the real machine. On the rotor side, we will connect a current sensors, and from there you are getting some current. You are getting what is the current. Okay, if I sense the current, I will get AC current here. This is rotor current. So if I get AC current, I am sensing the current. The actual current we are getting, actual current depends upon the power. The actual current will be calculated, and from there the pulses will be generated. This, I think, if you see here, there will be two everywhere. If you see D and Q, normally all the machines, I think if you are MTech, maybe you can understand. In BTech, I don't know, the DQ control was maybe not covered to you. DQ means, it's called synchronously rotating reference frame. There you convert your, it means normally if you, all those currents, they are rotating at 50 Hz frequencies. Yes, all those currents and voltages are rotating at 50 Hz frequency. Suppose the reference, if you are changing at 50 Hz, suppose if you are changing your reference also 50 Hz, then my reference is changing, my actual is changing. Then how it will look like? One from the another relative speed will be, my reference is at 50 Hz, my actual is 50 Hz. Both of them are going like this in sync. Then with respect to one, the other is stationary. With respect to one, the other is stationary. So normally all the quantities which are running in varying, if you change your reference from stationary to your synchronously rotating frame, all your AC quantities will be converted into DC quantities. Then your control will be easier. And also, all those machines, suppose if you take a DC machine, there will be torque. If you want to control the torque, you will control armature. Yes? If you want to control the flux, you will control field. Yes? Both of them are completely decoupled. You can control torque and flux separately. If I change my flux, means field, then my flux will change. If I change my armature side some current, my torque will change. So my torque and flux are completely decoupled. One is not depending on the other. In the same lines, even for induction machine also, you want to make it completely decoupled, flux and torque. That can be done with the help of this DQ transformation mostly. So D component is for active power, Q component is for reactive power. Suppose if I start increasing this reactive power slowly, suppose if I make it from 0 to 10 or 15, then this will inject the reactive power, this converter will inject reactive power, and it will not draw any reactive power from the grid. Okay. Now, one more thing here is, this is to maintain the DC link voltage. This is the converter control. And if you see here, there are one PI controller here, another second PI controller. Here you have two PI controllers here, 2 plus 2, 4. Here you have one PI controller, 5. Here you have one PI controller, 6. You have two PI controllers inside. Total there are 8 PI controllers in this to control this DFIG system. All those will be placed. You have to properly tune those PI controllers, and you have to place the digital signals to achieve this. This one maybe I'll go directly into hardware system. This is a hardware system that was developed in my PhD in IIT Delhi. This is the machine, wound rotor induction machine. This is DC machine. This wound rotor induction machine, you have slip rings. Those are coming out where, I think here the slip rings are taken out, and this is an encoder here to get the pulses. I think this is around, I think before independence, I think not before 1951 or sometime IIT Delhi was established. 1951 or 52, like that, around 60 years. At that time they brought it from London, UK, from where somewhere they got it, this machine. Still it's working, very good, very robust. These are only 3.7 kilowatt machine. Suppose if we see in your lab, maybe 3.7 kilowatt machine is maybe this much only, this much small. Now this is so overrated machine. It means for 3.7 kilowatt, even if you generate 5 kilowatt also, it won't, there will not be any problem. At that time, that is so, means overrated. You will have good ventilation, good air, and everything it will go. Then there is no chance of burning and all these things. Yes, this is the D-space. This is the one of the controller that is controlling everything. Here, these are the two converters I told, rotor side converter and grid side converter. These are the two converters, or otherwise maybe call it as inverter. These are the two inverters. Here you have all the sensors. I think you need 15 to 20 sensors to sense different voltages and currents. You have to sense the volt. You normally take the wire from here, and you normally sense here, And after sensing, you will have some signal conditioning circuits you have to prepare on your own, those boards, and PCB you have to prepare, and from there you will give to this uh, microcontroller or digital signal processor. It will do some computing inside. It will do it's like a brain. It's like a brain. It will tell, oh, my voltage is less. Now what I will do? Increase my duty ratio. If I increase my duty ratio, or otherwise modulation in terms of AC, if you talk, you have to increase the modulation. If you increase my modulation index you may have studied in inverter. Yes, in PWM inverter, modulation index. If my DC link voltage is fixed, if I increase my modulation scheme, my AC voltage will increase. Yes, like that. Actually, for doing that, so whether to increase your modulation or decrease your modulation, first of all, you should know what is the voltage. What is the voltage? For that, you need sensors. You need sensor. Here we have sensed everything, and after sensing, it will give to the displays and it will do the comparison. Here we will tell I need 415. Then it will sense, oh, 400 volts is there. Now increase my modulation. It will give some pulses, and this pulses will increase the modulation. This converter will operate at higher modulation, and you will get some different voltage. Like that. Here, this is what was left. This is the transformer to change the voltage, because in rotor, if you take the rotor voltage is slip times your stator voltage. Yes, so I told my slip is 0.3, so my 400 volts here from stator side, if I have 400 volts, my slip is 0.3, then the rotor side voltage is 400 into 0.3, 120. But in almost all the machines, you will have stator to rotor turns ratio. Most of the machines. In this machine, the stator to rotor turns ratio is 2:1. Again, so 400 is converted into 120, and due to turns ratio, again it will be converted into 60 volts. So in rotor side, you are getting 60 volts. So to boost from this 60 volts to 400 volts, you need a transformer here. This is a transformer here. These are all inductors. Maybe inductors are very small, but here these are general purpose inductors. Here it will have variable tappings. Suppose if I want 0.5 millihenry, if I want 1 millihenry, if I want 2 millihenry, like that, from 0.5 millihenry to 20 millihenry I can get, depends upon taps. If I come between these two, I will get one inductor value. If I get it come between these two, I will get different inductor value. Okay, this is in lab. I think we are different people. So many people are working. I may need different inductor value. Some other person may need different value. So these are general purpose inductors. And this is the grid that was connected. Even if you see here, we have taken power from the grid only, from the grid through this auto transformer. It was given to DC machine. DC machine will convert this DC machine was coupled to DFIG. It will convert mechanical energy to electrical energy. It will be fed back to this another auto transformer. It means the power was taken from this, from the same grid, the power was taken from this and converted into electrical to mechanical in this DC machine. And also maybe we can, with the help of this chopper, we have emulated wind turbine characteristics, and this was from this mechanical energy to electrical energy, and it was fed back to the grid again. I think I have done for around 3.7 kilowatt. I am able to send to the grid. I think just besides this, I think yesterday Sandeep sir's his setup is there. Just besides this setup only. Yesterday lecture was given by him. He is my senior. Okay. These are some of the simulation results I will show first. Then the hardware results. The wind speed is changing here. Suppose I take my wind speed is 8.5 or something like this meters per second. Then the rotor should run at a particular rotor speed for achieving MPPT around 0.9 per unit. The power that is feeding to the grid is 2 kilowatt. If you see here, the rotor currents, these are at different frequency as compared to your stator and grid. This is, the time period is less here, the time period is more here. If the time period is more means the frequency is less, because in the rotor you will have slip times frequency. Yes? Okay. Suppose this is at 9. Now the wind speed is exactly 9.2 meters per second I have taken. For that it has to run at exactly 1500 rpm. 1500 rpm means 1 per unit. 1 per unit speed it is running for achieving MPPT. If my wind speed changes, my rotor speed should change. Previously, if you see, my rotor speed is around 0.9. Now, if wind speed increase, so rotor speed increase. If my rotor speed increase, the power increase. It's more than 2.5 kilowatt power. And sorry, if you see rotor currents are, it's looking like DC. Rotor currents are DC because my slip is 0. If my slip is 0, my rotor frequency is 0. Frequency is 0. So it is like DC. So the DC current is injected into my rotor. When my slip is 0, rotor is. So this is again, if I increase my wind speed around 12, now my power start increase to around 4 kilowatt. Okay. Now, these are the real hardware results that were taken from using power analyzer. This is the voltage, 392 volts, exact grid voltage, and current is 4.6 amp. The first one is grid current, grid voltage and grid current of all the 3 phases. These stator currents, these are the converter currents. The power that is feeding to the grid is 3.08 kilowatt that was feeding to the grid, and we try to maintain the reactive power to 0. So this is the reactive power is 0, and so this is the kVA 3.08. And the current that is we are injecting into the grid, those are very I think you should there is a standard, the THD should be less than 5. So this is the THD that is injecting into the grid. Suppose grid current, this is D. This one is grid current phase A THD, this is phase B THD, this is phase C THD, and these are all stator THDs. All are less than 5%. If you 1.0, 1.1, 3.4, 2.6, 3.2. This is at different wind speed at 9.2 less wind speed. So here the power is previously 3 kilowatt, now the power is 1.73 kilowatt. Now the power was reduced as wind speed reduced. And even here also there is little bit reactive power, that was capacitor it is showing. It means little bit it's capacitive reactive power, not lagging reactive power, this is leading reactive power. And this is a stator power. If you see here, the grid power is, it is converter power is showing negative here, but if you see in this case, this is positive, this is negative. It means as you change your speed from below synchronous speed to above synchronous speed, the slip is changing from plus to minus. The slip is changing from plus to minus. If slip is changing plus to minus, then my rotor power will also change from plus to minus, because PR is rotor power is slip times your air gap power. Rotor power is slip times your air gap power. When slip changes its direction, the rotor power changes its direction. Previously that is plus, but this is minus, because as you are reduced the speed has come below synchronous speed, so the power was changed its direction. Sir, I think some problem. It's not detecting. సార్ ఇందులో పెట్టొచ్చా అవి ల్యాప్టాప్ లేదు, దీంతో పని చేయట్లేదా? దాంట్లో పెట్టింది, దాంట్లో పెడితే ఇక్కడికి వస్తుందా రాదా? ఓ స్క్రీన్ షేరింగ్ ఉండాలి ల్యాప్టాప్. ఓకే. ఆఫ్టర్నూన్ నాకు తెలిసి ఆఫ్టర్నూన్ సెషన్ ఇందులో ఓపెన్ అయినట్టు లేదు, అది వేరే మోడ్లో ఉంది, పీపీటీ మోడ్లో లేదు, కనిపించట్లా. ఓకే, ఇప్పుడు ఇలా కంటిన్యూ చేసేద్దాం. ఐ థింక్ బట్ దీస్ ఆర్ డిఫరెంట్. I think another 10 to 15 minutes. 12:30. No. Another 10 to 15 minutes. I'll finish. Okay. In class, if I tell క్లాస్లో చెప్తే వాళ్ళు చాలా ఒకసారి ఒక స్మైల్ ఇస్తారు, చాలా బాగుంటారు. మరో 5 నిమిషాలు వదిలేస్తానండి. ఆ స్మైల్ కనబడట్లేదు, మీ సార్కి భయపడుతున్నట్టున్నారు. ఓకే. ఓకే ఓకే, పెన్ డ్రైవ్. PSCMR. Okay. Okay. Again, these are the results that were captured in using oscilloscope, digital storage oscilloscope. There, the first one is this one. The first one is, I think this won't work. First one is change in wind speed. The first one is change in wind speed. Wind speed is, the previous results are steady state at a particular wind speed, but here we try to see never wind speed is constant. So we try to change the wind speed continuously. The first graph, this is changing continuously. If wind speed changes, then my rotor speed should change in the same way. This is the reference rotor speed that was given by my that microcontroller, and this was actual rotor speed that was sensed using an encoder. This is actual rotor speed is also changing. So the power that is feeding to the grid, this is grid power, that is also increasing. Each division is 2 kilowatt. So this is around 3 kilowatt power is feeding to the grid. And this is grid side converter, the power is changing its direction. Previously this is negative, now grid side converter power is becoming positive. With the change in wind speed, suppose you are going from below synchronous speed to above synchronous speed, the power in grid side converter reverses, and this is grid side converter power is reversing. This is stator power and grid power is grid power is increasing and reactive power is 0. If you see here, these are previous results are with respect to power. Now these are with respect to currents. This is the change in speed with the change in wind speed. This is stator current, grid side converter current. This is grid current. The grid current started increasing. So voltage, grid voltage is fixed. As current increases, power increases. Yes. Okay. This is rotor current. This looks interesting. As you are going from below synchronous speed to above synchronous speed, the power will reverse, I told, because slip reverses, slip become negative. Slip negative, power reverses. How power will be reversed? If my current phase sequence, if it changed from ABC to ACB, if my current phase sequence, previously ABC phase sequence is there, now if you multiply VABC, IABC, you will get some positive power. If I can multiply my VABC and IACB, the phase sequence is changed, ABC to ACB, now my power will be reversed. So for getting reverse power, the current direction was reversed. Previously ABC was there, now it has become ACB. Now one of the current has changed its direction, okay, from ABC to ACB. Now the power will be reversed. These were captured using oscilloscope. The real rotor currents of the machine was sensed. This is standalone. I'll quickly go through. Okay. In previous case, whatever we have discussed is for grid connected mode, but here standalone, I told, standalone means this was connected to load. Here there is no grid, so now our responsibility is to maintain the voltage. Previously the voltage was maintained by the grid, we are injecting the current, but in standalone you have to maintain the voltage. Here the maintaining the voltage is again one more work it has to do, but the thing is it need not have any PLL type of structure. So again the same thing, but instead of grid we have load. The control here is maintaining the voltage here. The voltage is maintained by using this VT. VT is the terminal voltage. It was maintained, and again the same scheme was used here, but here we have one more extra thing, that is battery. Most of the cases, if you use any of the renewable, it's better you should use battery, because if I connect suppose if I using for agriculture purpose, something, if I have solar, my pump will run, the water will be given, it's okay. But if I give the same thing to my home, then what, if I have solar, I will give supply to you. If I don't have solar, I will not give to you, means it's not fair. It's not fair, yes. So you should have something energy storage. So here we have connected battery energy storage system. This was battery that was connected. So when you have surplus power or more power than demanding power, then it will be stored. When you have less power, then this will be given. Even if you don't have power generation from this DFIZ, still this battery can give power to my loads. Okay. So most of the cases, I think in standalone, if you are using single renewable, it's better you should have energy storage. These are the power. If you see here, the load is non-linear, so the current is like this, but still my stator currents are very much sinusoidal. I have to maintain, because suppose if my current here is non-linear, then it will have some harmonics, and such a big machine, due to that harmonics, you will have harmonic torques, and the machine may vibrate. The machine may vibrate. So you should have sinusoidal currents here. So you will have sinusoidal current, but the harmonics current will be supplied by this converter. The harmonics current will be supplied by this converter. Here you have very non-linear current, and here you are making it sinusoidal or linear, and the harmonics part was supplied by this converter. See, this is the load TH 27.1%, but here our stator THD is still 2.6. It's maintained good. One more thing is, we have developed this, it's okay, good. These are hardware results, develop this. But if you suddenly put a single phase load, motor load, normally in house we don't have our water pumps. Will not have much starter type of arrangement. These are quarter HP, small HP motors, you will run on DOL, direct online starting. If you do direct online starting of induction machine, you will have high inrush current. If you have that much high inrush current, if you are taking from this, your voltage may collapse. So we try to check here, the motor was turned on, still your voltage and current was maintained. These are some of the results: increase in wind speed, and here the power is reversed here. In battery current, previously you have some at low wind speeds, battery has to supply, and once the wind speed has increased, the battery starts getting the power because you have extra power. I think it's enough. Anything if you have down, any query, something we can discuss. It's okay, sir. Sudden change in wind speeds. Thunderstorm. Thunderstorm, actually, if you have thunderstorm, the main problem is with uh, mostly electrical side. Mechanical side, it won't damage much, but electrical side, there may be some high voltage that is occurring, maybe surge arresters and all these things we have to take care of properly, because the high voltage strike is falling on, then you have to do the all those how our transmission towers we are protecting, like that we have to protect. Electrical. Changing the speed of the wind. The thunderstorm means that lightning only, na? Not. Sudden gust, wind gust is coming, sudden wind change. Wind speed change, you are telling. Wind speed changes, okay. At that time, mostly we try to do with electrically. In addition to that, in those extreme cases, we have to go for pitch control. Pitch control means the blades, we have to change its position, so that if wind speed, even if it is previously, if it is like this, suppose if wind speed is hitting like this one, it will rotate. Suppose if I change this direction, now the effect will be less. Direction and which, how much wind velocity is there. So yes. Depends upon every time, 24/7, the people is you have to, actually there are two ways. Already as well there is wind measurement. Wind measurement is there, but people try to avoid measurements mostly. If you have mechanical measurements, that may fail one or the other time. We never rely on that. Sometimes it need maintenance and all these problems. Normally it will be done with the help of electrical measurements only. You sense your voltage, you sense your current. From there, if you get the power, you will understand if that has crossed some threshold limit, then you will give command to your pitch control. Now, oh, something is extreme, now change your direction. Mostly we have to the whole control will be mostly on electrical side. For example, variable speed is there. So whether you are changing the whether you are changing the rotator speed of different wind velocity, you are changing. It is changing. So whether at the time of this sudden deep depression is coming, so whether you are continuously monitoring whether the changing of the. Yes, wind speed will be measured. Mostly we will have an anemometer. By that only we will decide. First of all, the thing is we will try to do the electrical control. Electrical control, if the speed has, there is clear indication to us. Suppose if wind speed increases, your rotor speed increases. If rotor speed increases, anyway we are sensing the rotor speed. The rotor speed, if we are sensing, then it will give command to pitch control. No, something is not fine. Now, there will be one separate called stalling condition. Stalling, STALL, stall condition. stalling condition, it will give command to stall your wind turbine. It will change its pitch control and it will be out of completely order, and your now it will not run. That will be always it will be there, because wind speed we never know. It may go very high, sometimes it may be less. That type of protective mechanism scheme will be there, obviously, in terms of mechanical.
So it depends upon that whether the people are whether the maintenance of this measurement of the speed with respect to the
Yes, yes, yes.
so obviously
They will monitor with the wind speed sensor, but the first thing, then suppose even if it fails, there is no problem, because now we have so much sophisticated algorithms are there, adaptive algorithms are there. You can exactly, approximately, you can get the idea by the help of voltage and current and everything. If you can sense voltage and currents, you will get the idea what is the wind speed and everything. There are some approximation schemes are there. Okay, thank you. Anything? No? Okay.
Thank you so much for the wonderful session, sir.
No, thank you.
After a short lunch break, the session will be continued by 2 p.m. Thank you.
Thank you. Thank you.
players 180 degrees మొత్తం 180 degrees విరిగిపోతుంది సార్